I'm gonna be the next presenter talking about a combination of research ideas that we have been sharing over years. So my job is going to be a little bit easier after both previous speakers, after Tom and Dr. Zahan, because they covered some of the topics that I wanted to talk about very briefly. So just like jumping into it so that we save some time. Hydrologic cycle, as you can see, it's a lot of processes happening there, and in the recent years we have been getting a lot of satellite observations and Earth observations which can tackle specific processes of this hydrologic cycle that we can use in order to have a better understanding or a better way of closing the water budget, closing the terrestrial water budget using remote sensing, where you can look into the increasing availability of satellite observations. As you can see, different ways of looking into radiation, short wave or long wave, surface temperatures, clouds, subland processes, and if you go on the other side, the evapotranspiration, evaporation, transpiration, soil moisture, precipitation, and runoff. A lot of different methodologies where you can employ remote sensing or the increasing availability of remote sensing data that you can use in order to address some of the issues and to be able to close that water budget. So as you can see here, over the years from the 80s until the recent and either some more future missions where you can see hydrological variables, either we're talking about atmosphere, total water, rainfall, soil moisture, wetness, vegetation, surface temperature, a lot of different instrumentation that has been going on and have been used in order to address some of these specific variables and specific parameters, and that helped us a lot in order to assess or to be able to have better understanding of the water budget, or to be able to have more accurate estimations. And that can be like an interest to precision agriculture, how we can maximize the usage of our current water resources.
استخدام الموارد المياه الحالية، فإن في مصر أكثر من 70% من موارد المياه تستخدم في مختلف القطاعات الزراعية، وكذلك هناك كثير من إهدار المياه، فلا بد وأن نكون أكثر محددين بشكل أكثر في استخدام المياه. من ضمن هذه الأمور كما ذكرت هناك كذلك بعض السلوكيات المشابهة والغريبة. ذلك هنا في شهر ديسمبر في كل العالم، فإنني أركز على شمال أفريقيا، وأركز كذلك على حوض النيل، حيث نرى هذه الإشعاعات المظلمة والحمراء، والتي تدل على أن هناك نوع من ارتفاع المنسوب أو ارتفاع الترسيب. وكذلك بالنسبة للون الأزرق يشير إلى ارتفاع المنسوب في أماكن أخرى. كما ذكرت هناك كذلك بعض الآثار لتغير المناخ. بالنسبة لملاحظات النتح فإننا ننظر هنا
the top 10 centimeters, all of these satellite observations using looking into NDVI, or Normalized Difference Vegetation Index, which is a variable measuring the healthiness or the greenness of vegetation. And all of these variables can be used in order to assess the amount of probable stress which can be present on these agriculture fields. GRACE experiment, terrestrial water storage, which can give you an idea about the underground water storage, and in areas where you don't have much precipitation, so you don't expect a lot of recharge. That's why you see some red spots towards northern of the basin. The scientific idea or the scientific background behind all of that is how we can look into the spectral properties or the spectral behavior of different targets. The whole idea depends on the usage of different regions of the spectrum. And in our case, when we talk about vegetation, we use the red spectrum and we use the infrared spectrum, where these two are very sensitive to different behaviors in the vegetation, and we come up with what we call NDVI or FPAR or leaf area index, and a lot of different variables, a lot of different indices that can be used to assess the degree of greenness, the chlorophyll content, the chlorophyll absorption. You can look into the scattering of the spongy mesophyll, which can talk about the leaf internal structure and how healthy or what kind of stress might be present. You can also look into water content, the amount of water present inside the leaves, also through specific channels, which can be very representative for water distribution. And looking into that, if you put it in a space where you have the near infrared and the red frequencies, you can really track the phenological cycle of plants, like early on when you have wet bare soil, as you can see here, and moving along this curve on the second plot from the wet bare soil. You have plantation, you have no vegetation yet, and then the intermediate canopy, almost striped. You have high canopy biomass, and in all of these stages, it all depends on looking into the behavior in the red and the infrared spectra. And you can end up with something like this, where you can really track like those different kind of colors that you are observing are for different crops, for sugar beets, for cotton, and also for alfalfa. And you can see the growth period, you can see the different stages, and at every single stage of these, you can really understand what kind of stressors might be present. Speaking about research and innovation, one of the most recent missions which have been launched by NASA is called EcoStress, and I'm not sure if anybody in the audience is aware of this mission, which was just launched 2018, and it is a sensor which is being placed right now on the International Space Station, and EcoStress is addressing like very important questions for the terrestrial ecosystems, and also commenting on the carbon budget. To determine how much water plants use and to study how droughts affect plant health. EcoStress is one of the sensors which is going to give us a huge amount of information about the temperature of the leaves, temperature of the plant. So basically when you have the stomata, and if there's any kind of stress or pressure on these leaves, it's going to close and it's not going to be breathing out. So basically when the temperature is increasing, you can identify how much stress is present on the plants. This is one of the couple of images that were acquired on Egypt using EcoStress. As you can see, it was acquired July 8th of this year. The yellow and the red indicate generally higher temperatures, like you can see here around the River Nile, and that dark image on the right-hand side represents some of the vegetation on both ends. One of the very important products from EcoStress is called Evaporative Stress Index, and this is one of the most comprehensive satellite images for detailed temperature for this region, which happens to be in Costa Rica. And you can see the level of the information about the temperature in this image is a very good representation of the stress on vegetation in this area. So advancement of technology, moving from the Landsat going all the way to Sentinel, and now looking into more detailed information. Like everybody talked about the pivot irrigation, as you can see here in Egypt, different locations. So I'm highlighting this as a red square over there. Look into this area. Let's zoom in a little bit more, and let's look into some phenological and crop development using Sentinel, which is 10 meters resolution. So you can see here the NDVI, or the Normalized Difference Vegetation Index, which is, as I mentioned, it's a measure of healthiness. It can show the greenness, and it can tell you a little bit about the stress. So when you look into something like this, you can see some daily variability of the phenological cycle which happens in these areas. These different distribution of colors are representations of need and demand, the need of water, or being stressed, or what kind of fertilizers. We can have maps like this for liquid fertilizers and as such. So it can really help in targeting specific areas, specific plants, specific crops, so that you can really be more precise in the water usage. Really advanced technology right now, which is the EcoStress, as I mentioned, and this is the only satellite image that ever exists for Egypt, showing you evapotranspiration, and you will be surprised to know that these two observations are happening at the same exact day. So you have morning evapotranspiration and afternoon evapotranspiration for the same day, before and after irrigation. So you can see those different regions which are highlighted like this, those blue ones. It's really actually after irrigation. So it can really be instrumental in addressing specific fields, and you can really think about that, how you can reduce the amount of the water usage, and how you can be very targeting at a very high level the kind of the need for water or for fertilizers. That's the first part of my presentation, where I just wanted to show very briefly some information about remote sensing or satellite observations, and how it can be used to address more efficient ways of using our current existing water resources. Our system or our Earth observations or the system that we are living in is quite complex. There is a lot of different kind of complexity. There is a lot of different interacting mechanisms that happen between atmosphere, hydrosphere, lithosphere, biosphere, and as such. So those kind of complexities require a different way of looking into the data, a different way of analyzing the data so that you can really get into the depth or in the information which might be embedded in the data or hidden that we are not really benefiting from looking deeply into it. Yesterday we got very great presentations from the speakers. I just took some snapshots for yesterday from Deltares' presentation, very long time series of the Nile flow, and you can see here representation of some stochastic processes and some probabilities, and looking into areas or regions where you have wet seasons or dry seasons, and in the images down below, just representing deviations from the norm. And doing that, you were able to highlight areas or time periods where you have really prolonged droughts or others which are quite wet. Tom did a very good job outlining the floor for me to talk about El Nino. He did it already. Nino is a global phenomenon which does have regional impacts. El Nino happens as a disruption in the connection and the teleconnection between land, ocean, and atmosphere. It's the interplay, it's the motion of the warm waters in the Pacific, east to west, west to east, which identify the two phases of El Nino, the warm and the cold phase. And when El Nino happens, as you can see, it does have an impact at a global scale, like different areas might be dry, different areas might be wet. Here in Africa, which is very interesting for me, if you look into this yellow band in the middle from July to September, you can see it is a dry region. This area gets affected by El Nino. And if you look a little bit down below, you're going to see another part of Ethiopia right there, which is wet. So the northern part is dry and the southern part is kind of wet. So there is an impact, which might also be of varying behavior, because the process itself is not stationary. So we cannot look into processes like this from station perspective. So another way of representing El Nino, as you can see here, different regions, different areas. Areas which might be under stress right now, which might be suffering from water stress, might be suffering from water scarcity in the future. And there has been a lot of things in media and news talk about El Nino, and African countries are urged to prepare for the rise in extreme El Nino events. So it is happening, and it will keep on happening, and maybe nobody is aware of what might be happening in the future because of these kind of disruptions which are happening around us. So looking into data, what we are observing here, we are observing precipitation data and soil moisture data over the whole Nile Basin countries, all of them, and you can see there is a lot of processes, a lot of noise present in the data. If you take a look on a time series like this, I think that the only thing that anybody, a very well-experienced eye, will be able to highlight maybe one cycle, one frequency, maybe seasonality. You might be able to highlight the increase and the decrease during a specific season, but you will not be able to identify any kind of hidden signals in this data which might be over a different time domain. Those kind of localized variabilities are very hard to pick, using conventional methods. So I chose to compare three countries, Egypt, Sudan, and Ethiopia, just for easier comparison, and because El Nino is affecting that eastern part of Africa more dramatically. The two charts down below are a representation of some of the indices, some of the parameters that we can use in order to assess the severity of the phenomena, and just to establish a kind of academic kind of the kind of work that we did in the past, similar to this. Some publications, some research work related to using rain gauge data, looking into El Nino in Virginia, as well as applications of recurrent neural networks in drought projections in California, a work which published last year, computational methods for climate data, and we are writing a book right now with Springer about computational methods for climate data with one of our elite mathematicians. So again, just showing you soil moisture data and precipitation data for both countries, for three countries. and we just want to analyze this data. So let's take a look into this precipitation data in Ethiopia, and we want to separate this time series into different independent physical processes. If you take a look into this time series, you will not be able to identify what are the driving forces, what are the driving physical processes which contribute into the different kind of precipitation variability. It is very hard to do something like this. So first thing to do, let's take a look at Fourier transformation. So I'm gonna get a little bit technical, I apologize for that, but it's gonna be short and sweet. So looking into Fourier transformation here, you can see that Fourier is able to identify the most dominant frequency, the biggest cycle, which would be like seasonality, something like this, where it would be like, half a year, a quarter of a year. So you can really look into something which is happening more frequent, but again, there is no stationarity in it. You cannot say that it's going to be happening frequently every single year in the same magnitude. So it's not going to be easy to identify that. And it's not a perfect sine wave. There is no physical process which is a perfect oscillation. This kind of oscillation varies over time and it changes over time. So it's very hard to do that. So the problems that we are facing with Fourier transform, perfect eternal sine waves, are unphysical. Like there is nothing which is a physical process which is perfect sine wave. Real physical process changes in amplitude and period over time, and that's absolutely true. They are going to be changing over time, and the amplitude is going to be varying over the years. So you don't expect to see this kind of stationarity, and we break the time into hundreds and thousands of these components. So it is not very efficient. So the FT Fourier transformation gives us good information about the frequency content in the global signal, like precipitation, global signal. So it gives you an idea about the frequency content, but with no localization. You cannot identify which part of the space contributed to which frequency component. So if you are able to identify a cycle which happens every season, every year, every 2 years, every decade, every 20 years, every 30 and 40, so these are different frequencies, you will not be able to identify something like this through Fourier transformation. So we move into wavelets, where wavelets can be a tool for analyzing localized variations of spectral power within a time series. So we end up with something like this, a plot that Tom showed something similar, where you can look into a band like this, and you can see that each horizontal line in a wavelet decomposition can represent the evolution of a physical process over time. So you can say, there is a physical process which is evolving over the course of time, and you can see, okay, in year 1980, this is what happened. In 1981, this is what happened. 1982. So now it is localized over the time. So you are able to really look into the physical process and see how it affects the whole signal at different time steps. And it's very nice way of representation, but again, we can do that qualitatively. We have to look into this in a way where, we need some expert eyes. But again, there is no means to extract this physical sub-process. If there is embedded in this signal something which happens every 2 years, or 3 years, or 4 years, or 10 years, how you are going to be able to identify such a physical process? And the answer is we do empirical mode decomposition. So here we go to EMDs, where we break down the time series into several physically meaningful components. And this is what we call IMFs, or intrinsic mode functions. So basically you are subdividing the whole time series into different cycles, into different frequencies, where each frequency might be driven by a different physical process. So it might be SST, as Tom was talking about, or NAO, PDO, SOI, and so on and so forth. So each signal is not stationary, its amplitude and period changes over time. So you can see each of these signals, the amplitude is changing over time, so it's varying. And it can be really a representation of the nature of the physical process, not just a regular sine wave, which is just a perfect oscillation, which never happens. There is no physical process like this. We get several components at qualitative different time scales, not thousands of components, because if I decompose it into perfect sine waves, it's going to be a lot. So it doesn't work like this. So when you look into something like this, if you add up all of these different IMFs or intrinsic mode functions, if you add all of them, if you sum them up, you end up with the same exact time series that you started with. So the precipitation data, this time change, this variable which changes over time, if I decompose it over different frequency domains and I add them up again, they will give you the same exact time series with no residuals. And this is how we interpret our components. Let me jump a little bit so that we don't go over time. This is a way of looking into what we call the Hilbert-Hwang transformation. So basically, if you take a look into each of these curves, you are going to see the colors are even changing. So you can see, like, for instance, the one that I'm highlighting, it's a signal which happens to happen at 10 years oscillation, like, from 4, you can see the vertical axis from 4 to 10, so like it varies over this time domain, and it happens to match with El Nino. But you can see also across the different kinds of components, you can see the relative power of each IMF. So those colors, some of them are getting darker, some of them are getting lighter. So it can actually tell you the impact of this physical process over that localized time. So I can say during that period, 1980 to 1985, I can see which IMF with which frequency is contributing to that system. Not only that, but I can also see the power of the contribution of that physical process into the whole time domain, or into the whole time series. So I chose 2 different IMFs. IMF number 3, which is the annual cycle. It appears to fade in and out relative to the strength over time. It's an annual cycle. And the 7, which is the decadal cycle. And you can see it fades after the year 2000. And this is for the precipitation over Ethiopia. So I took the IMF number 7, which is the one that we think it's very close to the SOI, to El Nino. And guess what? When we decompose the SOI data, which is the index or the measurement for the strength of El Nino, we have a correlation of 0.719. So there is a major high correlation between these 2 variables. So we say, okay, so Ethiopia 7, or this component number 7, is tracking a physical process. And the SOI number 8 is tracking a physical process. And these 2 processes happens to correlate very well. So it makes a lot of sense to say that they are highly correlated, which means that the SOI is driving the precipitation over this region in that kind of frequency, in that kind of decadal oscillation, or in that window, which is the 3 to 8 years. Doing the same analysis for the entire countries in the basin, we end up with a map showing you the correlation coefficient or the correlation behavior between SOI, which is the El Nino event, how dry it's going to be. The coastal regions are less compared to the one in the Central Africa, as you can see. So this is really a very important observation. And it made a lot of more sense to me after I saw the presentation from the second plenary yesterday, where I saw this graph, and I took a picture of it, which showed us the prolonged droughts. And I was not aware of this curve before. I just saw it for the first time, like everybody here yesterday. So I saw some years, 1972, 1984, 1987, which are the years identified below that line, which is known as how it is defining the drought. But I did a little bit something extra, which I checked these years. And guess what? All of these years happens to be El Nino years. And those El Nino years are not the only El Nino years. However, we have other El Nino years as well. So you have those circles that I'm highlighting are very common, known El Nino years as well, which directly will affect the whole system and would push this line where we are looking into the drought level to something which is much higher. So if we say that the 44 level is still actually to be defined as a drought level. So looking into that line, how the definition of the drought is 30-something BCM. This is way, way extreme, and it's not taking into consideration a lot of other events which happens to be also driven by El Nino. And this is the other line that I'm proposing. However, this is only by looking into one physical process, which is El Nino. So looking deeper into this and looking into actual observations, no modeling whatsoever, these are observations of soil moisture. And guess what? This is the whole SMAP data. The whole SMAP data record since it was launched until now, since 2010 until recent 2010, the three countries, green Egypt, red Sudan, and blue Ethiopia. 2010 and before, until 2012, it was a very dry period. And the soil moisture data is showing us that. Later on, starting 2012, you see a lot of peaks, and of course, you see some dips, because it is a non-stationary process. It will not be similar every single year. You're going to have outliers. One of them is like 2015, which is a massive El Nino, and you can see the drop in the precipitation and the soil moisture, but the whole period is a wet period. And like if you count the years, it's going to be like around 7-8 years. So by the end of 2021, 2022, I would say that will be the end of the wet period. And starting 2022, I would say this region is going to be suffering dramatic drop in water sources. And there will be severe droughts in this region. So moving forward, the El Niño cycle is going to kick in again, and you are going to be hit by a very dry period. Taking all of that, I have one more slide. Taking all of that into account and applied to future projections, so we used recurrent neural networks, where you can have nodes, like all these circles, like all these nodes before the event. So you are looking into a lot of physical processes. You have, this is application over California, where we had 100+ years of data. So we took 100+ years of data in order to teach our algorithms, like to learn from it. So the neural networks is learning from almost 100 years plus of data, and then we used around 15 or 20 years of data for validation purposes. The curve in the top is a representation of some validation data sets, where you have the dark line is forecasted, the gray line is observed, and you can see towards the end, 1997, 98, is a very known El Niño period, where you can see very high correlation between our model and the observed. This is an event which happened already. The one in the bottom was a forecast. We were projecting what's going to happen in 2015, 2016. So you will see towards the end of 2015, you are going to see two curves, the dark and the gray, which is the observed and the forecasted. And then you are going to see the rest of it is only the dark one, because we don't have observation. So the remaining part of that dark curve is just a representation of what we are projecting, what we are forecasting. So that's a prediction for the coming few months over California. And guess what? This paper was submitted for publication in March 21st, 2016, and it stayed under revision until December of 2016. So 9 months under revision. Because basically, like, you know, they were waiting for the season to happen in order to validate it, to see, like, actually, is it going to be raining? Like, are we going to really have severe droughts or not? And Tom is my witness here, because we live in California, and it was a very dry year, and the paper got accepted. And of course, like you can see the error bars towards the end, it's getting like wider as you move on, because like the accuracy is going to be dropping, and that's expected, but the first few months was very, very high accuracy. My take-home message, Earth observations can be used as a means to address water-efficient usage in agriculture, and the intersection between data science and Earth system science is quite needed, and it can really show us different information that we are not really aware of. Thanks for your attention, and I apologize. I was okay. Thank you so much.